Okay, so this is the last bit we're going to do on differentiation for a little while. We're going to look at applying the quotient rule to some trigonometry in this video, and then on the next one we're going to look at some other ways of differentiating trigonometry. Let's go! So just to remind you, we should be familiar with the basic rules for differentiating trig from the last few weeks. And last week we looked at the quotient rule, which is that if you have something that looks like a fraction, you can differentiate it using this gnarly little formula. So let's apply that all together. Y is tan x, what is dy dx? Well, what we're going to do is we're going to write tan as its basic identity as being sin x over cos x, and that's in the form u over v. So let's say u is sin x and v is cos x, and then let's differentiate them both. So du dx is cos x and dv dx is minus sin x. So far, nothing too controversial. We want to do v du. So the first one we want is cos times cos, that's cos squared. Take away, and then u dv. So that's minus sine times sine, that'll be minus sine squared. So we've actually got a minus minus in the middle there. Let's change that to a plus. And then what's about on the bottom? V squared is cos squared x. So that's looking pretty decent for our dy dx. But we can go one step further because cos squared plus sine squared is an identity, and it's an identity that's equal to 1. So we can just write this as 1 over cos squared x. And we can even go one step further than that. We can use our little reciprocal trig, or sec or cosec. This is 1 over cos. So the third letter has to be c. It's sec squared x. So if y is tan x, then dy dx is sec squared x, just using the quotient rule and things we already knew. And you can apply that exact same process to differentiating sec and differentiating cosec and all that stuff. I am going to work through this, but if you want to try it first yourself, I'd well recommend it. It's worth seeing if you can apply it. So here we go. Sec is 1 over cos x. So we're saying u is 1 and v is cos x. Then du dx is equal to 0 and dv dx is equal to minus sin x. So on the top of our fraction for our differential, dy dx, we're going to have v du, so that's just 0. Take away u dv, so that is minus sin x. So we've got another minus minus there, so we can change that to a plus. And to be honest, you probably don't need to write the 0, but we will do. And then we've got v squared, so that's cos squared on the bottom here. And obviously get rid of the 0, and we can say this is sin x over cos squared x. Now if you look up the differential of sec x, they won't tell you this. They'll actually have done some extra steps, so we'll show you what they are. We can split this up into the following: sin x over cos x times 1 over cos x. Okay, so obviously top times top will give me sine, cos times cos will give me cos squared. Now, why have I done that? Well, these can be rewritten. Sin x over cos x is tan x, and 1 over cos x is sec x. So if I'm differentiating sec x, I can get tan x sec x as my differential, or I think they normally write it as sec x tan x. Then we can try and do the same thing with cosec. Again, I'd recommend you have a go first, but let's go. 1 over sine this time. So u is equal to 1, v is equal to sin x, du by dx is equal to 0, dv by dx is equal to cos x. So if we're differentiating, we want v du, well, it'll be 0, minus u dv, so minus cos x, all over sine squared x. And obviously we can get rid of that 0, and we can say we've got minus cos x over sine squared x. But they're going to want to split this up again. And have a guess about how that might be. That's right, it's going to be cos x over sine x times 1 over sine x, because then we can put stuff in terms of reciprocal trig. We get minus, and this is a cot x, cos over sine, opposite of sine over cos, so it's 1 over tan. And then 1 over sine x is cosec x. So our differential of cosec is minus cot cosec. And the last one we can consider is cot x. Now you could actually do this, I think, with powers. You could use this as like tan x to the minus 1. suppose, and use some chain rule, but we're going to stick with the quotient rule for now. I think it's probably easier. Cot x, as we mentioned on the previous slide, is cos over sine. So we're saying that u is cos and v is sine, and we can differentiate them both and get minus sine and cos. What do we want to do with that? Well, we want to do v du minus u dv again. So our dy dx is going to be minus sine squared for the v du. Once that's not being cancelled out to a plus, take away u dv. So take away cos squared x all over v squared, so all over sine squared x. What can we do with this? Well, we can take out a factor of minus 1 essentially on the top, and we can say this is minus sine squared plus cos squared all over sine squared. And why might we do with that? Well, then that's that identity again. We know that this is equal to 1. So we can go ahead and say this is equal to minus 1 over sine squared x. And again, we want to write that nicer. So we'd say it's going to be minus, not sec, cosec squared x. So there we go. The 4 basic reciprocal trig differentiations, all done with the quotient rule. Now the good thing is that most of these are given to you in the formula book in the exam. So these 2 you have to go away and learn, but the other 4 they're ones that you can just read off the formula book. So you don't have to learn all of these, which is good. The other thing that's worth saying here is that we can apply all of our other trig rules here, so or differentiation rules. So we can use the chain rule, we can use the product rule, we can use the quotient rule, and it's just about, again, trying to pick out the right situation with these new bits of information. So what about if we were trying to differentiate tan 7x? Which rule would that be? Well, we're not multiplying anything, so it's not product. We're not dividing anything, so it's not quotient. It must be chain rule. And this is how we'd split it up. We would say that y is equal to tan u, and u was equal to 7x. So it's that function within a function. And we differentiate them both, which will give us sec squared of u, and du dx, I should say dy du, shouldn't it? There we go. And du dx is equal to 7, and then to get our differential chain rule, we just multiply those 2 things together. 7 sec squared u, which should be 7 sec squared 7x. There's our final answer. Okay, what about cosec of x squared? So this is one where the x is being squared, not the whole function. Well, we would say that y equals cosec of u, and u equals x squared. Makes sense to me. So we'll find dy du, which according to our list, cosec goes to minus cosec cot. So this will be minus cosec u, cot u, and du dx will be equal to 2x. So we need to multiply those 2 things together, and we'll get that dy dx is minus 2x cosec u cot u. Now obviously I want to get rid of those u's and replace them with the x squared, so everything is in terms of x. But yeah, it's just basic chain rule. What about these 2? Well, give them a go and unpause when you're ready. So these are both chain rules as well. This first one is the whole function that's being raised to a power of 4. So we would say that y is u to the power of 4, where u is equal to sec x. Now what would that mean? Well, it means dy du is equal to 4u cubed, and du dx, again according to our list, is equal to sec x tan x. And then we just multiply them together, same as we have been doing. So dy dx is 4, it says u cubed, so let's actually write sec cubed x times sec x tan x. Now you could actually bring those secs together, couldn't you? So we could say overall that is 4 sec to the 4 of x tan x. Ah, cool, it kind of contains its own differential. What about this next one? This is a bracket. It's something being raised to the power of 3 this time. And we're going to say that u is equal to cot 3x minus ln of x. Now dy du is straightforward enough. That's 3u squared times by the power, drop the power. But du by dx, you've kind of got to use a chain rule within a chain rule. Now, we did, I think, cot of 7x on the previous page, and we worked out it just stuck a 7 at the front of it. This is just going to stick a 3 at the front of it as well. But if you're not happy with that, you'd have to then say, well, u equals cot y, or maybe cot z, and z equals 3x, and then do another chain rule. But either way, you're going to end up with minus 3 cosec squared 3x from the cot 3x, and then the minus ln x is going to go to minus 1 over x, because that's what ln x goes to. So our overall answer here, we multiply these two together, so we'll end up with minus 9. Wait, no, we won't, because that whole thing, it's not 3 times the whole thing, it's just minus 3 lots of that. So we'll have 3u squared, so what the u? So we'll have 3 lots of cot 3x minus ln x squared, then times this minus du dx. So I might take the minus out and put it right at the front and then just use it positively. So yeah, we'll say 3 cosec squared x plus 1 over x. Probably a few different ways of actually writing that out, but that's the one that appeals to me. And then just so they don't feel left out, here's an example with some more quotients and some product rules. But again, remember, you get given these bottom 4 equations. You don't need to remember how to do them. You might need to prove how to do them. Actually, they might ask you, but they'll generally give you a bit of a hint. So first one, we have got a quotient rule. So our u is equal to cot x. We know it's a quotient rule because it's a fraction. U is equal to cot x and v is equal to e to the 2x. So that seems straightforward enough. Du dx is equal to minus cosec squared x, and dv dx is equal to 2e to the 2x. That's the exponential shortcut. Now, I want to use quotient rule, so we're going to have v du on the top, so that's minus e to the 2x cosec squared x minus u dv, so minus 2e to the 2x cot x. Doesn't look like it. I mean, you could take out a factor of minus e to the 2x, but I don't feel like it's going to make anything nicer. And then on the bottom, we'd have e to the 2x squared. You could simplify this a little bit, I guess. So like the bottom of this would go to e to the 4x, and the top, if we took out that factor of e to the 2x, we could then cancel that down. So we could go for a final answer of, we'd sort of like change that one to being 2x, wouldn't we? That would just be sort of eliminated. So you could eventually, yeah, you could differentiate it to that. I think that's as nice as you could make it. But yeah, the first answer is still right. And then our second one is a product rule. We can tell this because they're being multiplied by each other. And for a product rule, we want to differentiate each of them separately. So same thing again, du dx for sec x is equal to sec tan, and dv dx is equal to minus cosec cot. This looks like it's going to be a fun one. So we would have udv, because this is product rule now. So we'd have minus sec cosec, I need to put x in there as well, sec x cosec x cot x, crikey, plus v du. So plus sec x cosec x tan x. Very, very similar. So you could take out a factor of sec x cosec x, couldn't you? Let's do that. So we could say that is sec x cosec x, and then let's use the second term first, tan x minus cot x. That looks slightly nicer, I suppose. Yeah, there we go. Quotient rule with trig. Just make sure you know those formulas are in the book and that you can prove them if you need to.